All right, so I just missed the first part of this. Okay, so if we have, let's say, if we didn't have this extra charge here, I'm going to put the formal charge. Now look at the formal charge of this oxygen, right? The formal charge of this oxygen is 1, 2, 3, 4, 5, 6. Well, it gave 6, it has 6. So now this is neutral, right? But is this stable? This is not stable. This is going to be very reactive because, again, a free radical is called a dangling bond. A dangling bond wants to bond something to take electrons or oxidize something to strip electrons off. In the case for nitrate, it just takes that electron, and we have this. So, then again, why the heck is nitrate electron rich? It doesn't seem electron rich because when you look at this, I mean, this is negative, this is positive, this is negative. Where's the electron rich part of this? Well, maybe it is electron rich. It seems to be more electron rich than electron poor. But the situation is this. When we do electron rich and electron poor, it's relative to the atom. Oxygen wants an octet. Okay? And so oxygen like this is perfectly fine. So an oxygen with a negative formal charge like this is good. It's better than having a zero formal charge and a free radical. This oxygen's good here. Okay, so what makes nitrate electron poor? It's not the oxygens. The oxygens are perfectly okay, although these could react. It's the nitrogen. What makes nitrate electron poor is the nitrogen. But you go, well, it's only +1. That doesn't seem so poor, right? You seem formal charge is +1 in a lot of other things. But it's not the formal charge we look at in redox. What do we look at in redox? Oxidation states. And so let's take a look at the oxidation states. The formal charges I circled, the oxidation states I put in parentheses. What are the oxidation states on the atoms in nitrate? All right, what's the oxidation state of this oxygen? Remember, oxidation state, winner takes all. So who wins all the electrons, oxygen or nitrogen? Oxygen. So it ends up with 2, 4, 6, and both of these, so that's 8. 2, 4, 6, 8. How many did oxygen get? 6. So it ended up with 2 extra electrons, which means the oxidation state of this oxygen is -2. That's fine. Oxygen wants 2 electrons. If you look at the periodic table, if you look at the periodic table, oxygen is 2 electrons short of having an octet. Oxygen wants 2 electrons to be like neon. It'd have a filled second shell. So that's nothing unusual. I mean, oxygen -2 is stable. Think about what happens, what happens to oxygen and air and metals. When you have oxygen and air and metals, you can even see it on the stapler. Even though they tried to paint the stapler to protect it from what? Oxidation. But the oxygen and air is attacking the stapler and causing it to rust. Oxygen wants what? They wants 2 electrons. So when oxygen is -2, we don't call that electron rich. We just call that happy as is. It's happy as is because it doesn't want to lose those. It doesn't want to give those up. So oxygen at -2 is a very poor reducing agent. It's a very poor reducing agent because it doesn't want to lose those electrons that it gained to get that octet. Does that make sense? This oxygen is the same as this. And so this would be -2. This oxygen, though, is different. What's the oxidation state on this oxygen? It's different in terms of formal charge, but is it different in terms of oxidation state? No. So what is the oxidation state here? -2. So all these oxygens are happy as is. They aren't rich. They aren't poor. They're just where we expect oxygen to be. Think water. What's the oxidation state of oxygen and water? No, -2. The oxidation state of oxygen and water is -2. Do you call water electron rich? No, we don't. Well, electron rich meaning like a fuel, like methane. You know, think about methane. Methane is a great fuel. Oxygen is a great oxidizer. So we take a good reducer like methane and a good oxidizer like oxygen, and we get the flame. So this is good as is. What about nitrogen? What's the oxidation state of nitrogen? +5. Now, how many valence electrons does nitrogen have? 5. So this is essentially losing all of its valence electrons. So we start off here, we lose 5 electrons, and then eventually we're at helium. So nitrogen +5, think about successive ionization energy. Do you remember? Like I1 versus I2. I2, if it's a valence electron, is about double the energy. So when we ionize the first to the second, it's about double, and then it goes up like that. But when we hit the core, it's about 10 times more energy. The ionization energy is about 10-fold greater. So let's say we're looking at sodium. Sodium's ionization energy is fairly low. It's about 500 kilojoules per mole. But that's the one valence electron. Now, if we try to ionize the core, it's over 10 times the amount of energy. I think it's like 7,000 kilojoules per mole. You know, it's huge. So we aren't going to take that. No, this is about it. So we call this a mass. The oxidation state for nitrogen varies. Nitrogen is a really interesting compound because you find rich redox chemistry in nitrogen because the oxidation state of nitrogen varies from +5 all the way to negative +5 to -3. Now, how did I get -3? So the oxidation state ranges from +5 when I get to helium to -3 when I can get to neon. And all the numbers in between. And so this is like the range. We want to know with the minimum range, the maximum, we want to know that range. So nitrogen, +5 to -3. Do you know what oxygen range is from? Potentially? -2 to +6. Chlorine can range from, yeah, -1 to +7. Do you think chlorine's very happy in +7? No. Chlorine is extremely unhappy in +7. Have you seen chlorine in +7? Yeah. Yeah, you've seen chlorine in +7, which makes this particularly dangerous. This acid is particularly dangerous acid. And what is the acid? It's HClO4. HClO4 is a particularly dangerous acid because, let's take a look at the Lewis structure for HClO4. I'm going to do it without an expanded octet. I'm just going to leave it as the octet here in high formal charge. This has high formal charges, so typically we like to expand the octet to reduce the formal charge, and this is chlorine, so it's a rule rather than a law, let's say. And in this particular case, I'm not going to do anything. It's -1, -1, -1, and +3 on the chlorine. That's the formal charge, but we're looking at redox. So for redox, we don't deal with formal charges. For redox, we look at the oxidation state. And so what is the oxidation state of this oxygen here? This is a bridging oxygen. So we have a terminal oxygen here with a single bond. We have a terminal oxygen with a double bond. Now we have a bridging oxygen with 2 single bonds. What's the oxidation state of oxygen here?
0.
0 is correct. Or, no, the formal charge is 0. But the oxidation state is counted a little bit differently. It's winner take all. So who wins? Hydrogen versus oxygen. Who wins? Oxygen versus chlorine. Oxygen. Oxygen wins all these. 2, 4, 6, 8. It contributed 6. It's minus 2. This oxygen, minus 2, minus 2, minus 2, which makes chlorine plus 7. So the oxidation state on this is plus 7, which makes this electron poor or electron rich? Electron poor. It's very poor. Perchlorates are very dangerous. Perchlorates are powerful oxidizers. And if you have a reducer like this, like, you know, ammonium, is that electron rich or electron poor? Well, a lot of people see the positive charge. They see a positive charge and they think electron poor. But it's not. It's not, even though that positive charge goes on nitrogen. Let's take a look at the Lewis structure for this. Or you don't have to do this by Lewis structure. We could also do this by formula. If we do this by formula, this is in chapter 3 or something like that, or book. We assign hydrogen first. What's the oxidation state of hydrogen in compounds? Plus 1. What's the oxidation state of nitrogen? Well, 4 times plus 1 is plus 4. Plus 4 minus what will give us plus 1? Minus 3. So there's nothing unusual about hydrogen in the plus 1. We see it all the time. What's the oxidation state of hydrogen in water? Plus 1. Is it electron poor? Is water a pretty good oxidizer, like chlorine, oxygen? You know, the answer is water is pretty unreactive. But the nitrogen here, we looked at that. We'd focus on the nitrogen because the nitrogen would be electron rich. And so take a look at this. At one end of the spectrum, nitrogen is plus 5. This is as poor as it can get. So this is going to be the best oxidizer. At the other end of the spectrum, nitrogen gained 3 electrons, so it's like neon, 10 electrons. This we call electron rich. Electron rich. So we gotta keep these. If we don't want a reaction, we gotta keep them separate. So if I have something that's like really electron poor, like this, we got to keep it separate from electron-rich species, unless you want something reactive. Sometimes they want things that are reactive. Things that are reactive would be like this. A thing that would be quite reactive would be this. Rather than having a hydrogen, you know, if I have hydrogen here, that hydrogen is already plus 1 here. So can the chlorine take the electron from the hydrogen? No. And then we have these oxygens here. Will the chlorines take the electrons from the oxygen? No, unless it gets very hot, then it could, potentially. But there was a plant in Nevada that used to make this, or maybe they rebuilt it. But what is this called? Ammonium perchlorate. Now this is especially stable or especially dangerous and potentially unstable. Yeah, the only thing that's preventing this from reacting is it's trapped in the lattice. And so what we have here is this. This is electron rich. This is electron poor. And it's going to maintain this. This is called metastable. It's going to maintain this because the ions are trapped in the lattice and they can't interact. They're in their lattice position, right? But what happens if you heat up the lattice? If you heat up the lattice, you're going to get more vibrational motion. And if you continue to heat up the lattice, eventually those ions can collide with one another. And if they collide with one another, what do you think is going to happen? The electron poor species is going to attack the electron rich species, and we're going to get a reaction. So you don't want to get this hot. That would be very dangerous to get this hot because you don't want that kind of reaction to occur. The same thing with this. This one looks scary too. This one looks very scary. This is a solid. The only thing, okay, keep it cold. This one is also very scary. Why? This one's very scary because ammonium is electron rich. Nitrate is electron poor. So this nitrogen is +5. This nitrogen is -3. That's 8 electrons difference. Going from +5 to -3 is 8 electrons. So this nitrogen has all the electrons. This nitrogen has none of the electrons. And so if these two nitrogens got in a tug of war, what's going to happen? There's going to be a reaction, right? And so ammonium nitrate, this stuff doesn't look so great either. Versus sodium nitrate. Sodium nitrate, I'm not going to worry because sodium ions, does it have any electrons to give up? No. So sodium nitrate is fine, perfectly stable. Ammonium nitrate, no. Not so great. And so let's take a look at a couple of... I wasn't expecting to show this. So I haven't looked at the video in a while. This is it. I have to find the right. Audio. I guess the audio is not working. It's more dramatic if you can hear the sound of the explosion, but I can imagine.
It still looks great.
Similar explosions have happened in the U.S.
Texas City, with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products, you can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? 50 years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It was very strange. I'm really glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
When you look at it, you go through the watch. And there were townspeople by the hundreds. At night, behind the part of our parking lot, there was the ship. They came down to watch the fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
As you can see, there's some pieces of paper bagging going up over there in the way. And my boss thought, and I thought too, that we were witnessing a nitrate fire. But someone said, it's a grain ship. The grain's on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, the Monsanto secretary, was watching from her office window. And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster. The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We had a truck up here on the road. We had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City.
That's what I pulled from that. Come on, kids, we're going on a field trip. You're going to go watch something burn. Really explosive burn. Part 2 has veterans video. Charles Hadlock.
Spend much time in Texas City.
to look for it. Before I wasn't planning on showing that today. You should check out part 2. There's more details about it. But anyway, actually, I know what I was going to show you one other thing. Well, this is a perchlorate plant in Nevada. You know what? I don't get copyright violation.
Like this, you're about to see some of the most astounding moments of destruction ever caught on camera. This is destroyed in seconds. In the town of Kingston, Nevada, a chemical fire ignited at the rocket fuel manufacturing plant shut down. Over its heard. With every second that passes, the fire grows. What they don't know is that the inferno now threatens the storage area where 6 million pounds of rocket fuel is held. If the chemicals exceed 716 degrees Fahrenheit, the entire area will combust. Then, unforgettable.
The voice of the day.
As the explosion erupts, a powerful shockwave careens across the landscape, and a car traveling along the adjacent highway is caught in the blast. Multicolored smoke indicates volatile chemicals continue to burn. Moving on to question, did the blast detonate all of the rocket fuel inside the plane? The explosion is massive. Its shockwave completely decimates this building. The blast is so strong, it registers an earthquake measuring 3.5 on the Richter scale, 600 miles away. 2 people were killed in the massive explosion. What we are looking at is $100 million worth of destruction. These skeletal remains used to be a chemical manufacturing plant that produced rocket fuel for the space shuttle.
Okay. But, yeah.
Stuff like that burns, right? Chemicals aren't lost with the law of composition, and that's going to be long. It's going to end up settling down.
Yeah, exactly. What happens is when you have something like that, you have different levels of flames, like this. The situation with this is these are solids, and these solids, when they react, they produce lots of moles of gas. And so what you see are like detonations where there's a shock wave, let's say, and that's due to just tremendous amount of gas being produced in a short period of time, and lots of energy. And so that's what caused a lot of the destruction. If it just burned and just inflamed, then, it wouldn't have caused so much death and destruction. Like the Grand Camp, I think 600 people died in that explosion, including all the kids that were lined up to watch it. Yeah, and all the firefighters, obviously, and lots of townspeople. So that's why they say that's the worst man-made disaster in the U.S. Yeah. But that's in part 2. You could hear about that. And there's stories of the survivors in that. But anyway. So when we see this, you're thinking very dangerous, right? Very dangerous because you want electron-rich next to electron-poor species. So normally in chemistry, we separate them. You put the electron-rich over here and electron-poor over there. You don't want them to mix, I've had explosions in this lab, unfortunately. Yeah. I had a student in Chem 1B making up a lab. So I said, okay, we're making a lot of lab. The previous lab we used reducers, ethanol. Ethanol is a good reducer. What's a good reducer? Things that burn easily are a good reducer. So the last lab used ethanol. And in the current lab that we were doing, we were using powerful oxidizers. Nitric acid, powerful oxidizer, sulfuric acid, moderate oxidizer, a bunch of oxidizers. I think even chromate, No, we still call it. It's historically, it's always been an oxidizer. So you might not have any oxygen around. Like, for example, we don't need oxygen to burn methane. We can burn methane using fluorine easily, and that'll produce a big flame, everything else. In fact, fluorine's really dangerous stuff because fluorine is a much more powerful oxidizer than oxygen. And so, remember, was I talking about steel wool in this class? Yeah, steel wool has a lot of surface area. But you know what could light or ignite a steel bar? If you had fluorine gas. If you had fluorine gas rather than oxygen gas, you wouldn't need steel wool, which has a high surface area. You could just get a bar of steel and ignite it. And so fluorine gas is also very dangerous. I used to work with fluorine gas when I was at UCLA. And I wear I had all stainless steel. What we do is we passivate the stainless steel. Passivate it, that is, let the fluorine attack the stainless steel. When it attacks it, it puts a coating on there, which makes it more resistant to further attack. But the problem is not everything can be passivated. So I was using valves, and the valves I was using had a Teflon seat. Teflon's pretty unreactive. And so the valves I'd have to replace maybe once a week or once every 2 weeks. But one time, I was going off to shut the valve on my fluorine line, and I wore 3 pairs of gloves. And as I reached to shut off the valve, my glove just caught on fire. Boom. And then I realized I have a fluorine leak. So I shut it off and then replaced that valve. But the fluorine tank that I was using, we stored it in a steel box. So if there was ever a leak in the tank, it would have to eat through the steel box. And so the steel box was so that you had enough time to run away, basically, from the fluorine. So it gave you, and it's high pressure fluorine gas, so it's pretty dangerous. But anyway, going back to this, you don't need oxygen to oxidize things. You could have a flame, you can burn things, and you don't even need a gas. So, for example, in a lot of compounds, they can generate a flame just using nitrate instead of oxygen, or perchlorate instead of oxygen. There's no oxygen here, and we can get these to burn easily. We just don't want them to detonate, That is, you get this very violent reaction in a short period of time, which these ones do. Okay, those were the reactions. So redox chemistry, one of the things is redox reactions are high energy. They aren't the same as metathesis. Metathesis, you're looking at precipitate. Whenever you form a precipitate, let's say you even form a great precipitate. I'm going to form a really great precipitate. Are you going to worry about some explosion occurring when you precipitate? Acid base. You take a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. Are you going to worry about an explosion as you're titrating? That strong acid and strong base is going to explode in my face. No. But for redox, you're going to worry. If you take a strong oxidizer and a strong reducer, you're going to worry about an explosion. And so the student, what happened was, I told her, don't pour the ethanol in the oxidizer waste. There's a separate jug that you're going to pour the ethanol in. Make sure you pour it in that. But in the rush of trying to make up this lab and a whole bunch of stuff going on, and the lab was crowded, there are lots of people, the student accidentally poured the ethanol in the oxidizer waste, and the bottle exploded. So fortunately, just first degree burns, No eye damage, which is good, and hair was singed. But it was inside the hood, so there's a blast shield on the front of the hood. But the student was the blast shield was up like this, and the student was a little shorter and was trying to pour it in, and they stuck their face into the hood like this, and then it exploded. But the explosion, it was really lucky because it was a glass waste bottle, but the top was open, because of the funnel there. And so what happened was this huge fireball in there and a big bang, but most of it, the energy went up here and not out. If it went straight into their face, it would have been disastrous. So got lucky there. Yeah, you got to watch out for those. There's Zumdahl, who's one of the authors of a very popular chemistry textbook. I was listening to one of his talks, and he was giving a demo using thermite reaction. Thermite reaction generates a tremendous amount of energy. And he had like 5 rows of school children in a big auditorium. And the thermite generates molten iron, a very, very hot molten iron. So he had a catch tank with water in there to catch the molten iron. And so as the thermite reactions really, I could show it to you too. Thermite, have you seen the thermite reaction? Thermite reaction, think about aluminum. What is aluminum? Aluminum solid, is that a reducer or oxidizer? Reducer. And then rust. Rust is Fe2O3. Oxygen is happy as is. This is solid rust. Oxygen is happy as is. But what about iron? Iron is, what's the charge on iron here in rust? +3. Take a look at the chart. Iron +3 is what? Iron +3 is a pretty good oxidizer. Like here's nitric acid, here's silver ion. Silver ion is a great oxidizer as well. But the problem is this is a very strong lattice. So the iron 3 is kind of locked in the lattice, so it's not very reactive. Okay, for thermite, what we do is we heat this up. Once you get the aluminum to melt into a liquid, then this reaction takes off. In fact, this reaction becomes very violent once that aluminum melts. How do you get the aluminum to melt? You just heat it up, right? And so, so this is a redox reaction, but you think, okay, aluminum is a pretty good reducer. Iron 3 is a moderate oxidizer. But take a look at this reaction. I'm going to back it up a little bit. Oh, we lost.
It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The atom is the densest parts of the cup. It's basically a huge lump of metal, and well, it's very hard to move. Lucky then, the brain acts have plenty of thermite, specially packed into the slow release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bullet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clean through, it seems only fitting to have a go at the peasant tank. Packed into the slow-release mechanism of a carbon fire pot, the thermite is ready for action. Popped onto the roof, directly above the fuel tank, with its top up, and just 4 feet of family car stands between thermite and 8 gallons of petrol. Light the touch paper and stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. It's 2,500 degree heat, igniting the expanding petrol in a devastating fire. Moving behind the car that won't be going very far anytime soon.
Okay, so what happened was all that molten iron. He was planning to catch in a water bucket down here. But when the molten iron hit the water bucket, it superheated the water, creating superheated water steam, and that steam just shot off red hot iron fireballs and sprayed the first 5 rows of kids. They said that there were 40 fire trucks there and triage units and a whole bunch of stuff. It was very bad. So he said he stopped doing that as a demo.
I wonder why.
Yeah, that was. But yeah, fortunately, I think most of the kids were okay. But think, no safety goggles or anything like that. That's pretty scary. So we have to really watch out. One of the things is this. I told you how I classify chemical reactions, right? All redox reactions show a change in oxidation state. When we change in oxidation state, the behavior changes dramatically. So I was walking around, I saw some people write Na. That's fine, but Na means sodium metal. Na does not mean sodium ion. There's a huge difference between sodium metal and sodium ion, actually. Have you seen sodium metal react with water? There's one more video I'll show you. And then maybe that one. Yeah. Have you heard of Lake Lenore in Washington? Lake Lenore in Washington is one of these volcanic lakes. And there are no fish in there. And the pH and other things that make it not able to support any water. So they pick this lake to dump the sodium metal in it.
Pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium trickles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The accurate clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
So basically, sodium metal, very dangerous, very powerful reducer. Sodium metal is such a powerful reducer. Powerful reducers lose electrons easily that even water can oxidize it. Normally, we don't think of water as being a very good oxidizer. In fact, water is pretty unreactive. It's very stable. Look at planet Earth. You know, what, over 70% water, right? Pretty stable stuff. But if you react it with like something like sodium metal, then we have to think, what's electron poor in water? Is it the oxygen that's electron poor, or the hydrogen that's electron poor in water? What's doing the oxidizing? What atoms in water are doing the oxidizing of the sodium metal? It's the hydrogen. What's the oxidation state of the hydrogen? +1. I told you +1 is totally normal. Yeah, it's totally normal. It doesn't react with much of anything. However, you know, it depends on what you react it with. If you're reacting it with something like sodium, which is extremely reactive, then maybe we got to worry about it. And in fact, we do have to worry about it, because what's going to happen is sodium metal will lose that electron quite easily. Sodium forms a metallic lattice, but let's just take a sodium atom with a Lewis dot structure like this. It takes that electron. Once hydrogen takes that electron, it makes H. But H is not stable. It likes to make H2. So we make H2 gas. The H2 gas, once it gets hot in air, it explodes. So you see the violent explosions there. But here is a case where, you know, the oxidation states, yeah, we're getting a feel for this, and we need to get a feel for how things react. So what we need to do is this. The situation is, chemistry is a combination of, you know, because the theory is quite complex. Quantum mechanics. You do quantum mechanical calculations, very difficult. So what we rely on is a mix of theory. You know, we try to do some theory, because the more theory we know, the less we have to memorize. But it's not enough. So we have to do a combination of theory and empirical observation. And so those empirical observations will give us reference points in our mind. So somebody says, oh, +1, you know, what big deal? Sodium ions are +1. Are those a very good oxidizer? No, those are very bad, you know? So we need to have some kind of reference frames for this. You know, for example, tall mountain. You know, somebody told me, oh, you know, there's some mountains there. But when I looked at those, I thought, those aren't mountains, those are little hills, you know, but in their perspective, those are big mountains, you know. And so we need some kind of frame of reference, like what's hot, you know. If somebody says it's hot, you know, what is their limits, you know, the max, min, this kind of thing. So we do the same thing here. And the way we do this is by taking empirical observations. Those empirical observations are just, you know, little bits of factual knowledge. And so we generate that, and we try to generate this factual knowledge to help us place our what we do is like semi-quantitative or semi-qualitative theoretical analysis of things. And so it's a mix of experiment and theory is what we do. Experiment are just the observations. So experiments are just like watching a video like this or doing something like that. And so we get some kinds of perspectives. Yeah, normally water is very unreactive unless you react it with something like this, which is very violent. And so the situation is in redox reactions, the oxidation state changes. So you go from sodium metal, and then we end up with this reaction will form sodium hydroxide and hydrogen gas. The hydrogen gas can go on to explode. This is not balanced. But we end up with sodium ion. Now, sodium ion is no big deal. People put that on their French fries and eat it. you know, but nobody would be putting sodium metal on their French fries and eating that. That would be disastrous. And so the thing about redox is there's huge changes in energy and stability when you change the oxidation state. Whereas in metathesis and acid base, the oxidation states don't change. And so all you're doing is you're making stronger bonds or weaker bonds. You guys estimated delta H of reaction using the bond enthalpies. The bond enthalpies of the reactants minus the bond enthalpies of the products. That's it. And so you're making a little stronger, a little weaker bonds. You're making a little stronger lattice, a little weaker lattice. You know, but you aren't going to get any explosion based on that because the oxidation states don't change. And so redox is much more energetic, potentially, than acid base or metathesis. And so we treat redox reactions differently. And in fact, that's one way of recognizing these. So let's see. We'll probably take a break now, and then let's take a break. We're talking quite a while. And then